All right, here we are in the chapter called Fluids. The word fluid comes from the word flow. That means this includes both liquids and gases, since both liquids and gases can flow. And in this chapter, we're going to look at such concepts like density, pressure, buoyancy, Archimedes' principle, and Bernoulli's principle. Important concepts they are. So let's get moving. First of all, look at the difference between solids, liquids, and gases. Solids, they have a definite structure because of the molecular forces or the atomic forces are strong, and that gives it a basic size and a basic structure. Now, when you come to liquids, the molecular bonding is weaker, and therefore liquids do not have a particular shape. Of course, they have a particular volume, but they take the shape of the container. And move on to gases. The molecular forces are so weak that neither do they have a size nor a shape, which means you can put them in a big container and it will go to the corners of the container. That means it will just spread out. So that is the basic difference between solids, liquids, and gases. Now, gases can flow, as you can see here, and one of the basic properties of substances is the definition of density. Density is nothing but mass per unit volume. So density is mass divided by volume, and it's defined in kilogram per meter cube. Now, here are the densities of a few substances. The most important density that you need to know, which is our standard, is the density of water. The density of water is 1000 kilogram per meter cube, or 1 gram per centimeter cube. So that's the density of water. But you have densities of other materials here, like aluminum is 2.7 times 10 to the 3. And if you look at liquids, you see that blood has a density just a little bit more than that of water. It's 1.05 times 10 to the 3, which means it's 1050 kilogram per meter cube. And of course, the density of gases is much, much smaller. You can see oxygen is 1.43 kilogram per meter cube. Well, carbon dioxide is a little bit more dense, so 1.98 kilogram per meter cube. Now, while we talk about density, we should also remember that there is another quantity called specific gravity or relative density. Now, specific gravity is nothing but the density of the substance divided by the density of water. So, for example, knowing that the density of aluminum is 2700, its specific gravity is going to be 2700 divided by the density of water, which is 1000. 2700 divided by 1000 gives 2.7. So the specific gravity of aluminum is 2.7. And specific gravity does not have any units because it's just a ratio. Let's work out a problem on specific gravity or relative density. In this question, a bottle has a mass of 35 grams when empty. So that's the mass of the bottle alone, and 98.44 grams when filled with water. When the same bottle is filled with another fluid, the mass is 88.78 gram. What is the specific gravity of this other fluid? Now, the idea in this problem is that both water and the fluid, they have the same volume because they fill the same bottle. So you can find the mass of water in the bottle by getting the difference between 98.44 and 35. And likewise, you can get the mass of the fluid by taking the difference between 88.78 and 35. And these two masses will be for the same volume of the fluid. So here's how you calculate this. The specific gravity of the liquid is defined as the density of liquid divided by the density of water, like I explained before. And so density is mass by volume. So mass by volume of the fluid divided by mass by volume of water. Now this is the mass of the fluid. This is the mass of water. And the volumes, of course, get cancelled. And so you get the specific gravity of the liquid as 0.8477. Remember that specific gravity does not have a unit. Our second concept is that of pressure. Pressure is defined as the perpendicular force acting on 1 meter squared. So pressure is defined as the normal force or perpendicular force per unit area. Or in other words, pressure is just force divided by area. The unit of force is Newton. The unit of area is meter squared. That makes the unit of pressure Newton per meter squared or Pascal. Now, how do we find the pressure due to a liquid? To find the pressure due to a liquid, just imagine that there is a container here filled with a liquid up to a height h. Let the area of the base of the container be A. And therefore, the volume of liquid in this container is area of the base multiplied by the height, which is AH. If that's the volume, the mass would be volume times density. Because remember, density is mass by volume, which makes mass volume times density. And then the weight would be mass multiplied by G. So that's what you find here. The weight is mass multiplied by G, that which is, volume times rho times G, which is what you find written here. Now remember that volume is A times H. A times H. And so you get the weight of the fluid as rho AHG. So rho AHG. And this weight is actually acting on this area. And the weight here is the force. Therefore, to find the pressure, all we need to do is divide the force by the area. And the force is the weight, which was rho AHG divided by the area. The areas get cancelled, and so you get the pressure exerted as rho Hg. Now that is the pressure just due to the liquid column alone. But remember that the atmospheric pressure is acting on the surface of the liquid. So if we call the atmospheric pressure P0, then we know that the total pressure is going to be P0 plus rho Hg. So that's the total pressure acting. Now, this simply means that as the height of a liquid column increases, the pressure also increases. Well, the Pacific Ocean at its deepest point is about 11 kilometers deep. That's 11,000 meters. So, if you were to calculate the pressure there due to the liquid column alone, you would have to go pressure at the bottom of the Pacific Ocean. Density of seawater is about 1025 times the depth of the ocean there, like I said, is 11 kilometers, which is 11,000 meters, times 9.8. This would give you 108,825 pascals. Well, that is the pressure just due to the liquid column alone. Now, if you consider the atmospheric pressure, which is 101,325 pascals, and I'm going to explain this as we go along. If you add that atmospheric pressure to this, you get 210,150 pascals. So that is the total pressure at the bottom of the Pacific Ocean, where it is deepest, and it is 11 kilometers deep. All right, now let's talk about the atmospheric pressure. We may not realize, but we are actually standing at the bottom of the atmosphere when we are on the ground, and it exerts a huge pressure on our bodies. And this atmospheric pressure can be measured using a barometer. And the first barometer was constructed by an Italian scientist called Torricelli. And all he did was he took a tube containing mercury. This tube is filled with mercury, and then inverted into a container with mercury in it. He found that the mercury does not flow out completely. Instead, when he measured the height of the mercury in the tube, it was about 76 centimeters. Remember that this end of the tube is open, but yet the mercury is not coming out, which means it is the atmospheric pressure that is holding the mercury in the tube. The atmospheric pressure is actually holding it in the tube, counterbalancing its weight. Therefore, we can say that the atmospheric pressure is equal to the pressure exerted by 76 centimeters of mercury. So, to calculate the atmospheric pressure, we just need to calculate the pressure due to 76 centimeters of mercury. The height is 76 centimeters, which is 0.76 meter, times the density of mercury. Density is very high for mercury. It's actually 13,600 kilogram per meter cube. It's the density of mercury multiplied with 9.8. That gives you 101,325 pascals. So that is the atmospheric pressure. All right, this is just a review. We've already said that the total pressure is going to be the atmospheric pressure plus the pressure exerted by the liquid. And how can we measure pressure? Pressure can be measured using a barometer, that is to measure the atmospheric pressure. Now, what if you wanted to measure the pressure due to a gas in a container? Well, in that case, we would use an instrument called a manometer or a manometer, which is basically a glass tube shaped like a U. So, you see that when both are open to the atmosphere, Since the pressures are acting equally on both sides, the liquid will be at the same height in both the limbs. But when you connect it to a container with a gas inside and you want to measure the pressure of the gas here, you see that that pressure is going to push this liquid column down, which means push the column up in the other limb. And so by finding the difference in heights between the liquid levels there, you can calculate the pressure to be H rho g. Now that is the pressure difference. That's not the actual pressure. To get the actual pressure, you have to add the atmospheric pressure. And when you add the atmospheric pressure, what you get is called the absolute pressure. So the formula is that absolute pressure is always the atmospheric pressure plus the measured pressure. And the pressure is measured using a gauge, so that's called the gauge pressure. All right, let me make that clear. The gauge pressure is H rho g. If you add H rho g to the atmospheric pressure, what you get is called the absolute pressure. That's an important formula to remember. So here is a question now. The gauge pressure in each of the 4 tires of an automobile is 240 kilopascals in each of the 4 tires. If each tire has a footprint, which is the part that is touching the ground, of 220 centimeters squared, estimate the mass of the car. So what's given is the gauge pressure, and here is how we're going to do this problem. The weight of the car is actually balanced by the pressure in the 4 tires. So the weight of the car, which is mg, is equal to 4 times the force. See, remember, pressure is force by area. Therefore, force is going to be pressure multiplied by area. So that's why you have pressure times area. But there are 4 tires, so the weight is balanced by the force in the 4 tires. And so rearrange that. When you rearrange that, you get the mass is 4 pa by g. The pressure is 240 kilopascals. A kilo is 10 to the 3 or 1,000. And the area is in centimeters squared. You have to change it into meter squared, right? So 1 centimeter squared is 10 to the negative 4 meters squared. That is why 220 centimeters squared here is 220 times 10 to the negative 4 meters squared. So remember, that's in meter squared. That is in pascals. And that's in meter per second squared. So you get the answer as 2.2 times 10 to the 3 kilograms, which is 2200 kilograms, which makes sense for the mass of a car. Here's another question that goes, what are the total force and the absolute pressure on the bottom of a swimming pool 22 meter by 8.5 meter, whose uniform depth is 2 meters? What will be the pressure against the side of the pool near the bottom? So you got to find the total force and the absolute pressure on the bottom of a swimming pool 22 meter by 8.5 meter, and whose uniform depth is 2 meter. Now remember that the pressure depends only on the height of the liquid and its density. And once you get the pressure, you multiply it with the area of the base, you could get the force. So that is what is being done here. And also remember that you'll have to add the atmospheric pressure with the liquid pressure to get the absolute pressure. So the atmospheric pressure is 1.013 times 10 to the 5. That's the atmospheric pressure. Density of water 9.8 is G, and H is the depth. When you do all that, you get 1.21 times 10 to the 5 pascals. That is the absolute pressure. Now, how do you get force? Force is pressure times area, correct? Because pressure is force by area. So when you rearrange that, force is going to be pressure multiplied by area. So you get force is pressure times area. You multiply that pressure that you have with the area. What's the area of the base? It's 22 by 8.5. So it's a rectangle. Multiply those, you get the area. And so you get that big force, which is the weight of the water there is 2.3 times 10 to the 7 newtons. Now here is an interesting problem. You have a house at the bottom of a hill that is fed by a full tank of water, 5-meter deep, and connected to the house by a pipe that is 110 meter long at an angle of 58 degrees from the horizontal. Determine the water gauge pressure at the house. B. How high could the water shoot if it came vertically out of a broken pipe in front of the house? So this is a house at the bottom of a hill. And this could be something like that, and the water pipe is 110 meter long and at an angle of 58 degrees from the horizontal. So the water pipe is like that, making an angle of 58 degrees, something like this. And we have to find the water gauge pressure at the house. Now, this could be a better diagram, as you see there. You see that the house is here, and the pipeline is 110 meters. The angle is 58 degrees. So you have this height. And from this figure, you can see that, if you take sine 58, you're going to get H by 110. Okay, therefore, H is going to be 110 sine 58. That is the height. And you also have to remember that there is a 5-meter depth for the water tank. Okay, and therefore the gauge pressure is actually the pressure exerted by the water in the water tank, which is going to be 10 to the cube 9.8 110 sine 58. That's going to be the gauge pressure there because of this height difference. That comes out to be 9.6 times 10 to the 5 pascals. That is the gauge pressure. And now we go on to the B part. The B part says, how high could the water shoot up if it came vertically out of a broken pipe in front of the house? All right, so how high could it shoot up would be the total height. And the total height is nothing but 110 sine 58 plus 5. So if a pipe here breaks, the water is going to shoot up by that much. So water is going to shoot up exactly by that same height. All right. So the exact height, that is 110 sine 58 plus 5. So that is how we do it. Now here is a question that uses Archimedes' principle, which is the principle that gives you the buoyant force, and it is equal to the weight of the fluid displaced. So when you put a solid in a fluid, if it floats, and then surely it is able to displace its own weight of the fluid. Now, if it can't do that, then it's going to sink. But whatever be the case, a solid has a buoyant force acting on it, which is equal to the weight of fluid displaced by it. Now I'll repeat that second part, which is very important. Buoyant force is equal to weight of fluid displaced. Weight of fluid displaced is equal to buoyant force. Now this is the principle used in hot air balloons. In this problem, we have a spherical balloon that has a radius of 7.35 meter and is filled with helium. So it's not hot air, it's filled with helium. Now, how large a cargo can it lift, assuming that the skin and the structure of the balloon have a mass of 930 kilogram? Neglect the buoyant force on the cargo volume itself. All right, so the first step in this problem is to find the volume of the balloon. How do you find the volume of the balloon? It is said to be a sphere, and the volume of a sphere is 4/3 pi r cube. So if you plug in the value of the radius, you're going to get the volume of the balloon. Then if you multiply the volume of the balloon with the density of helium, you can get the mass of helium, right? You're going to get the mass of helium. And also, if you multiply the same volume with the density of air, you're going to get the mass of air displaced, because the balloon is displacing its own volume of air. So when you multiply the volume of the balloon, which is the volume of air displaced, with the density of air, you are going to get the mass of air displaced. Now, why are we finding the mass of air displaced? Because if you multiply this with g, this quantity with g, then you get the weight of fluid displaced. Now, remember that weight of fluid displaced is the buoyant force. So weight of fluid displaced is the buoyant force, and if you multiply this quantity with g, you are going to get the weight of fluid displaced. Now, do we have other stuff here? Yes. We have the mass of helium, to which we have to add the mass of the cargo, and we also have to add the mass of the skin and the structure, which is given as 930 kilogram. So you see that the total mass that has to be carried is the mass of helium plus the mass of the cargo and the mass of the skin and structure. That is the mass to be lifted. That means that should be equal to the mass of air displaced. So that is the principle of flotation, that if the mass of the floating body is equal to the mass of fluid displaced, only then can this body or can this object float. So that is the idea in this problem. So let's move on and see how to work this out. The total weight, here it is, the total weight is equal to the weight of the balloon plus weight of helium plus weight of the load. You can either take it as mass or weight. The only difference is weight is mass multiplied by the acceleration due to gravity. Okay, so the total buoyant force is the weight of air displaced. Set them equal to each other, and you see that the g's cancel out. So here you have the mass of air displaced. Here you have the total mass to be lifted. That's all. Problem done. And I told you that the volume is 4/3 pi r cube, which you can see here. And I've just done some math to show that that's the density of air, that's the density of helium, and I've taken out this volume common. That is the mass of the skin and structure. There you go. When you do all the calculations, you get the mass of the cargo to be 920 kilograms. Let us do another problem to make this principle clear. A scuba diver and her gear displays a volume of 65 liters. So that is the total volume of everything included. And they have a total mass of 68 kilograms. A. What is the buoyant force on the diver in seawater? Will the diver sink or float? Okay, how do you find the buoyant force again? Buoyant force is equal to weight of fluid displaced. Weight of fluid displaced. And what is the weight of fluid displaced? It's the volume of the fluid displaced multiplied by the density of the fluid. What is the fluid in this case? Of course, it is the seawater. Okay, so we will find the buoyant force by multiplying the density of seawater with the volume of fluid displaced. And the volume of fluid displaced is exactly the volume of the object. So that's how you do it. And that is a simple enough problem which we can do quite easily. So here you have it. The buoyant force is the weight of fluid displaced, which in this case is water. That's what the subscript stands for. That is the density of seawater. That is the volume, but it's converted into meter cube because 1 liter is 10 to the negative 3 meter cube, or 1000 liters make 1 meter cube, same thing. So when you do that, you get the answer as 653 newtons. That's the buoyant force. And the B part says, will the diver float or sink? Here's the answer. What's the weight of the diver and her gear? 68 times 9.8, which is 666 newtons. So the weight of the diver and her gear is more than the maximum buoyant force, and therefore she will gradually sink. Why gradually sink? You see that these two numbers are really close to each other. Therefore, you could even find the acceleration. That's interesting. You could find the acceleration because if you find the net force is going to be the difference between them. 666 minus 653, which is 13 newtons. And if you divide that by her mass, the total mass, you are going to get the acceleration, and that is 68 kilograms, right? So that's approximately 1/5 or 0.2 meter per second squared, which is small. So you see that the acceleration down is really small, and that's why I said that she will gradually sink. Hope that makes sense.